Okay, great. Thanks, everyone. I apologize, my voice is acting a bit up. Yeah, I would like to talk today about the 3 important players in observed and simulated climate variability and how they interestingly interact. And I started a little bit with a history, and I hope I don't have too much overlap with something I saw in some abstract that will come up in this week. But let's just start with a spatial map here of sea surface temperature. And of course, it's one of the key metrics that we use to characterize the state of the climate system, controlling large-scale atmospheric circulations, the distribution of life, and so on. Now, if you look at the variability, and that's here characterized just by the standard deviation of the SSTs at each grid point, we see this very rich spatial structure and these very interesting patterns, and some of those might of course be familiar to you. Just highlighting here the tropical Pacific, home of the El Niño southern oscillation, just here showing an illustration of the impacts that it has on weather system across the world. Now, the question is, what is causing SST variability actually in other regions? So you might be interested in the Indian Ocean or the Gulf of Alaska, or maybe the subtropical Jaya just north of Hawaii. Now, I want to argue here that there's really 3 key players that are important. So stochastic air sea fluxes, the seasonal cycle, and the El Niño southern oscillation. And that's what I call here the climate trio. And I'm going to go through a hierarchy of conceptual climate models, starting from going through the history, and that I will want to argue is that succinctly describe the observed statistics of climate variability from subseasonal to decadal timescales. Now, I'm going to start with stochastic climate variability, and of course, well, to start with the original Hasselmann model proposed in 1976. Now, in this simple formulation, can in the ocean look at it as terms of a box model, a bucket model, where we have a temperature, a mixed layer temperature tendency equation, and there's a right-hand side forcing term that's just white noise. There's a stochastic fluxes due to atmospheric variability, so just your day-to-day weather. And then we have a constant damping rate of the SST anomalies back to 0, which is again through the heat fluxes. Now, in this simple model, of course, we neglect advection in the ocean, so just like a local process. Now, the remarkable thing is that this model describes the statistics of observed variability rather well, and it's just a classic diagram here showing the power spectra of the leading principal components of surface pressure and SST anomalies in the North Atlantic. And of course, the surface pressure here, the atmospheric variable is white with a constant spectrum with variance distributed equally across all frequencies. And then we see, if we look at the observed SST anomalies, that they follow quite nicely the predicted spectrum from the Hasselmann postulated model. Now, of course, this model has been very critical in the development of statistical, of building the foundation for the detection of the human fingerprint in climate change, which is part of the work that led to Hasselmann receiving the Nobel Prize in Physics last year. Now, moving to the next step, increasing a little bit in complexity. If we look at the El Niño southern oscillation, this kind of AR1 model might not be sufficient, because when we look at the SST anomalies here in this region, just by doing a box average of the SST anomalies, you see this quite distinct oscillating nature, and you might, just by looking at it, see that maybe you might be detecting some periodicity here with your eye. And so in red are the big El Niño events, and in blue the anomalous cold events, La Niña. Now, what is driving these SST variations? We need 2 ingredients. The first one, a fast positive feedback. That's due to the coupling of the ocean, the atmosphere, and the tropics, which was postulated by Walker and Bjerknes in a seminal 69 paper. And then to get an oscillation, we also need a slow adjustment, and that's here the equatorial ocean heat content or the thermocline depth. Now, if you put these two things together, what Fei-Fei Jin did in his paper in 97 is you can include these two processes, and you arrive at a simple coupled two linear ODEs. The top one being the temperature tendency for SST anomalies in the Eastern Equatorial Pacific, and then a second equation for the heat content on the equator, or zonal mean thermocline depth anomalies. Now, these coefficients here, just written generally as those A coefficients, they can either be obtained from actual physical principles, or you can also empirically derive them from observational data. Now, of course, this kind of model has one of the type of solutions. It's just a limit cycle, a periodic oscillation, where these SST anomalies and thermocline depth anomalies are in quadrature. And now, this is kind of a nice base model because it is very simple in its essential dynamics, but we can add complexity to make it more realistic and describe what we see in nature better. So we can include deterministic nonlinearities in it, non-constant coefficients, and or multiplicative noise. And because we can then add those components and understand the dynamics that emerge if we add this complexity. And if you're interested in this in more detail, we wrote a recent review paper that's in this monograph, EGE monograph, where we go through the different aspects of this. Now, let me move to the seasonal cycle. And the seasonal cycle interacts here with two players, one with the stochastic climate variability. And if we go back to the original Hasselmann model here, the next extension to it, where we add complexity by considering the seasonal cycle, is this extension that was proposed by De Elvira and Lemke in 1982. And they expanded this model by adding a seasonal cycle in two components. One is adding a seasonal cycle here in the damping rate. And in this very simple form, it's just a cosine modulation here of the damping rate. And this is, you can argue, think about physics that lead to that. And partly one reason is the seasonal cycle of the atmospheric variability and associated the depths of the mixed layer going through the seasonal cycle in the extratropics. Now, you can also include more complexity and consider what happens to SST anomalies in following years, and there's a mechanism proposed by Clara Dessa on reemergence that plays also a role. Next, there's a seasonal cycle in the noise forcing, and this is quite naturally to include here because we know that the atmosphere exhibits a lot of strong seasonal cycle and its variability, with the storm track in the northern hemisphere being most active in the winter season and being more quiescent in the summertime. Now, we discuss the importance of these seasonal effects a bit later, so I'll come back to those. Also, the seasonal cycle plays a very critical role in the El Niño southern oscillation, and here there are two aspects to it. One that's related to ENSO's teleconnection or its impacts on the rest of the climate system. So what we can do if we are interested in the atmospheric response to those SST anomalies that I showed you is just a standard empirical method, just doing a principal component analysis on the wind anomalies, and what comes out here as a leading mode is this shown here in vectors are the surface winds, and then in colors is the zonal wind anomalies. So this is a weakening of the winds near the equator in the central Pacific, and this is just this canonical pattern we see during El Niño when we have the Eastern Pacific warming, we have convection shifting towards the east, and we have this weakening of the trades due to the changes in the Walker circulation. Now, you can just, because this wind response is directly related to the temperature, to the SST anomalies, you can just write a very general form of this, just your response variable y, which is here maybe the wind, is just linear related to your SST anomalies by this using this linear regression form with beta relating those two variables. Now, if we look at the second empirical mode that's orthogonal to the first one, we see this interesting pattern that has a lot of important features that are critically important in terms of impacts. One being this anomalous low-level circulation in the Northwestern Pacific that has very strong impacts on the East Asian monsoon system. And then we also see this southward shift of the anomalous winds that's also critical for actually the termination of El Niño events. Now, we can find that you can describe this pattern that it's also related to the SST anomalies, but to get this pattern, you need to actually consider the seasonal cycle. So it's just written here, a simple cosine that's an amplitude modulation of the SST anomalies that gets you this pattern. Now we can combine, though, like if we interested in generally in the impacts of El Niño, we can just write them as this general form. There's just a constant component here, and then there's a seasonal cycle modulated component. Now, the linear ENSO impacts have the same time scale as the ENSO forcing, and that's quite easy to see here, of course. But then what about the second part, the seasonally modulated impacts? And it's also simple to see that actually, because you have this this cross term here, that you generate this sum and difference tones to this amplitude modulation, which in this case, if you have the annual cycle frequency and the interannual signal, relate to this kind of near annual variability, which are the side bands on the seasonal cycle. Now, actually, it's very interesting because if we look at a lot of phenomena related to climate, we see this ENSO combination mode actually everywhere, and those timescales are really ubiquitous in the climate system. So this is just a few examples listed here, and but let's move now to the next step. So the seasonal cycle also plays a critical role within the ENSO system in its internal dynamics. And if we go back to this very simple formulation of this recharge oscillator, this two linear ODEs, we actually, to reproduce the observed ENSO characteristics, that is that El Niño events tend to peak in boreal winter, we actually need to include more realism here, and that is that the growth rate of ENSO depends on the seasonal cycle. So that's determined by the changes, the seasonal changes of the background state. Now, again, we can just write it. It's very similar as this simple. We write this constant coefficient just becomes this coefficient again that has a constant and a seasonal cosine here. Now, if you include this non-constant coefficient here in this recharge oscillator, actually does a really nice job at reproducing the observed characteristics. So here on the right-hand side, this is in bars, just a distribution of variance over the calendar months, and we see that we have increased SST variance, again here in boreal winter. And also, because we have, again, this cross terms here, we generate these near annual time scales also in the SST spectra. Now, what happens when all of these things come together? And in this case, we might want to consider an ocean outside of the tropical Pacific that's just integrating ENSO teleconnections. So this is and seasonally modulated ENSO forcing, and also noise. Now, we had the Hasselmann model, we had the extension with a seasonally modulated damping rate, and now we can add one more term here on the right-hand side, and that is both the linear and the combination mode ENSO forcing here on the right-hand side. Now, outside of the tropics, we can just imagine this. What we see is this Rossby wave train, of course, in the atmosphere. And then if we come back to our bucket model, we have the same dynamics here. We have heat fluxes that are stochastic, but then also we have heat fluxes that are due to the changes in the atmospheric circulation due to those remote ENSO forcing. And now, if we move within the tropics, I showed you before there's these shifts in the Walker circulation and also to some degree in the Hartley circulation that are important for ENSO's impacts. Now we can look at one example here, the Indian Ocean. So the Indian Ocean is home to a climate variability called the Indian Ocean dipole, which is a zonal dipole and SST anomalies, similar to what we see in the tropical Pacific with El Niño. And this is very critical because it shifts rainfall patterns across the Indian Ocean, impacting rainfall and drought patterns across all the rim countries, including the Horn of Africa, where we've seen drought now for several consecutive years. Now, we can write actually a time tendency for the time evolution of this mode of variability here in the Indian Ocean, the IOD, and that has three parts, one being a seasonal modulated damping rate, and there is very strong physical evidence due to it, because also in the Indian Ocean we have a air-sea coupled feedback that varies in strength through the seasonal cycle. We have seasonal modulated atmospheric noise here, and then we have these seasonal modulated ENSO teleconnections coming from the tropical Pacific due to shifts and Walker circulation. Now, the interesting thing is that this model really reproduced the observed ENSO IOD statistics well. And one interesting feature is if you look at this, so there's a plot here on the right, and just focus on those bars. Those are the the lead-lag correlation between ENSO and the IOD. On the right-hand side is the IOD leading, on the left-hand side is ENSO leading. And you see that the correlation is actually maximized when the IOD is leading ENSO by 3 months, and then we see another negative, a maximum negative correlation about 15 months when the IOD is leaving 15 months. So coming back maybe to what Christian talked about earlier, we often interested in causality in the system, and in this case we know the causality because here ENSO is on the right-hand side providing the forcing, and there's no feedback of the IOD back to ENSO, but nevertheless we get that actually the IOD is leading ENSO by 3 months in this lead-lag correlation, not by 15 months. And that's only due because their growth rate has a different seasonal cycle, leading to a variance maximum of the IOD in boreal fall, whereas it's maximized for ENSO in boreal winter. And then also the strong autocorrelation of ENSO that's here in the line plot, just meaning that an ENSO El Niño event typically leads to a La Niña event the next year, which explains that 15 months lead of the IOD. So this brings about this really non-intuitive result, maybe that, of course, we know the correlations don't mean causation, but I think a lot of people are tempted if they see leads or lags maybe to infer causality, but that you cannot do this because you just, if you distribute your variance differently in the calendar year with these interannual modes, you automatically get leads and lags, but they don't tell you anything about the correlation. Also neatly, if you look at the power spectra, here there's 2 lines, one from the observations in black and one from red, from a long integration of a climate model, is that you see this enhanced variance at these near annual timescales here designated by 1 minus FE and 1 plus FE associated with this combination mode. Now, this is interesting to understand the physics of the system, but this is also important. We have actually shown in 2 papers that we can beat operational IOD forecasts, which are of critical importance, using this simple model here and just putting in on the, we can derive all those coefficients empirically from the data and from physical considerations, and then plug in on the right-hand side the model predictions from the seasonal forecast systems for ENSO, and predict the IOD based on that. And we beat the IOD prediction actually in the actual dynamical model, because the models have so many biases in not getting the IOD dynamics right, the coupling between ENSO and the IOD in the model. But if we know that this empirical relationship and we can predict ENSO, we can also predict the IOD. Also, actually, this results moved us to, I think, at least think about refocusing our attention to the tropical Pacific for understanding global patterns of climate variability. And we have a few case studies where we look at different regions in the tropics and these different empirical modes of variability, the IOD, the North Pacific Meridional mode, the North Tropical Atlantic, and also the Atlantic Niño. And we can use the same framework to reinvestigate the driving forces of this variability and look if there's actually a feedback back to ENSO. And we can, this is a lot of ongoing work, but I think we have now the framework to do this carefully. Now, I want to just end here with a summary. So we started with the classic Hasselmann model, and then the ENSO recharge oscillator model made the 2 most simple but powerful models that we use in climate that describe a lot of the variability we see. And then we talked about 2 extensions of them that are important. One here, the D'Elvira and Lemke model, and then including the seasonal cycle in our understanding of ENSO, once we had teleconnections, and then also within the internal dynamics of ENSO itself. And then if we put all this together, we come up with this model that is quite neat for describing a lot of the variability outside of the tropical Pacific. And this includes things like spectra, lead-lag correlations, and so on. And then finally, I think this has a strong implication. I would argue that we have some support to say that the predictable signal of climate variability outside of the tropical Pacific is almost entirely due to ENSO. And that we know, because we know that ENSO is in current climate models looks good, but it looks good for the wrong reasons. Actually, the dynamics are completely off, that we really need to focus our efforts to get ENSO right for the right reasons, to say anything about its impact, both in terms of seasonal forecasts, but also in terms of future changes, and its it impacts on everything outside of the tropical Pacific. So yeah, I want to make just a pitch that ENSO is not solved, and we really need to look to the tropical Pacific. And then actually coupling this model on the top right with the ENSO recharge oscillator model gives us a really nice tool, because we can change those coefficients or fit them to different models to look then really at the expected statistics that come out of it and compare it with what the models simulate. And it's a really powerful tool that we use now in several papers. And yeah, using this to ground truth our understanding, as I think it's critical. So with that, happy to take any questions.
Timing, thank you, Malte. Question, Yugon?
Thank you for the nice talk. So in your model for between the IOD and ENSO, so you formulate a similar model to consider the interaction from the IOD to ENSO. So have you ever checked this so that whether the interaction between or the impact of the IOD to the ENSO is really negligible?
Yeah, so actually we have now been doing this actually for all the modes in the observations and all the climate models, and we haven't written this up yet. But yeah, I think we have quite strong evidence that the feedback is typically less than 10%, like for these modes of ENSO back. And so to first, I mean, there are some corrections of this simple view, but I think this is, I think, our starting point, and then we can build on this framework to include the feedbacks to learn more about those physics. But I think in this hierarchy, I first wanted to start without this feedback and then adding it back, and we can then compare the observations and climate models and see if they line up.
Thank you.
Sergey?
Just a technical question, because I missed, unfortunately, the first minutes of your talk. This T, ENSO, is that a vector, or what is it?
No, in this case, it's just this just the Eastern Pacific, like it's just averaged SST anomalies in a box in the Eastern Pacific.
So is it a scalar? Or
scalar, yeah,
yeah. Thank you.
Yeah. So to first order, yeah, we can just consider it this, but if we want to consider diversity in ENSO's pattern and its spatial variability, actually we need at least one more degree of freedom. Yeah.
So if I may make a suggestion, we have now this 3 million year transient simulation with the CSM model that has all these modes included under various orbital conditions. Would you be interested in diving into this and see how whatever these coefficients change, and whether you can really test what Jürgen suggested, the bi-directional effects in more detail under much wider range of statistical let's say, situations.
Yeah, definitely. And I think, I mean, there is, because all these coefficients depend on the climate state and the RC coupling that's due how the state is now. So I expect those to change, of course, over time. So this will be then also critically important for proxy records in variability in regions of teleconnections. So I think we might have positive and negative interference of these teleconnections, and I think, yeah, that would be yes.
Okay, if there are no more questions, let's close the session. We are just in time, 4 o'clock. Thank you to all the speakers, and thanks to the online audience for joining.